All right, can you hear me? All right, excellent. So my name is Thore Graepel, and I had the good fortune that indeed I did this, this doctorate in philosophy with specialization in computer science, and then I did get hired by this wonderful place. And one thing you might not even believe is that they actually let me work on my favorite topic, which is games. And I don't know if any of you like to play games. Can we have a little vote here? Yeah? Okay, games are pretty popular. So they're fun games, and I got to work on a couple of those. For example, has anyone here played Halo 3? Can I see you showing of hand? Now that's really strange, because I happen to know that this is the age group 12 to 14, and that has a rating of 16, I seem to remember. Still anyone up there who has played it? Ah, okay, very brave. Yeah, so pretty early on, after I had joined Microsoft, we realized that when we were playing Halo, somehow the system didn't seem to get our skills right, because it always seemed to think that we were weaker than we actually thought we are. Do you have that with rating systems sometimes? They just don't get how good you are? Yeah, have we got that? Yeah, it's a typical thing. And so we decided that we needed to improve that and develop this system TrueSkill, which is now in operation on Xbox Live. So that was good fun. But we also tackled a different problem, which is more on the kind of on the calmer intellectual side, if you like. Although I don't want to diminish the intellectual challenges of games like Halo. And that's the game of Go that Andrew had mentioned before. It's a very, very complex game invented in China 3,000 years ago. And if I don't have time to talk about it now, but if you want to play it, we have a game called The Path of Go on Xbox 360. And it's an arcade game, and you can download it. And it would be great if you could try it out and give us some feedback. Right. And that's a file browser in our Windows operating system. And I'm not going to talk about it. But the question is, can games also be useful? You know, we got some stats about Halo and Xbox, and we found that people spend billions of hours in total on those games, and some people might think that's a waste of time. So can games also be useful? And there's going to be two perspectives. One is that of the engineer, and the engineer might ask, can we use games to make people work for us? And in fact, this has been done. For example, we would like humans to do certain things for us that computers are still fairly bad at. For example, labeling images. You know, we show them an image, and they tell us what's on that image. Computers are not quite perfect at it yet, but we would like to generate examples for them to do it. And a guy called Louis van Aan, another computer scientist, developed the ESP game, which pits two people against each other in labeling an image and creates a game around that. And so hundreds of thousands of images have been labeled using this mechanism. So that's definitely something we can do. But we can also use games to find out more about how people tick, what they do, how they behave. And that's more the perspective of the scientist, of course. And I'm going to talk a little more about that here. So one thing people would like to do is find out how people behave. How do they behave when they're under stress? How do they behave when you offer them money? How do they behave in strategic situations when they are in conflict with others? And traditionally, this has been done in a lab. What you can see here is a bunch of relatively uniform people, not even that many. Those are the ones you can get into the lab, a fairly artificial setting, and then you can find out how they behave. But one recent article highlighted that this is actually pretty weird, because most of these people that we get into those labs are typically westernized, educated people from industrialized, rich democracies. Short, weird. And we would like to overcome that little bias that these studies have. And so our vision is to use Facebook as a lab. Can I just ask, is there anyone here who has heard of Facebook? Aye, all right. Is anyone here on Facebook? Okay, that's pretty much approaching 100% here. Very good. So in total, there are now roughly 800 million people on Facebook, and that should be roughly the largest lab that we can use on Earth. And we're trying to tap into this, and we also get this great diversity of people who are on that. And so we're aiming to do our research there. Now, the game we've picked for our first project is called the Colonel Blotto game. And if someone who likes Halo would also like Blotto, because it has a slightly military theme, but really it is a simulation of how people might assign resources, if they have finite resources, to different targets. For example, an advertiser might want to decide in which cities to place their ads, or a presidential candidate might want to decide in which state they want to spend their money for campaigning. So let me explain how this game works. There are 5 battlefields, as you can see here, and we have 2 opposing colonels or armies. And each side of each of these colonels can distribute 100 troops among these 5 battlefields. And the side with more soldiers on a single battlefield wins that battle, and the side that wins the most battles wins the war. Right? That's how these things are decided. I'll give you a little example. Suppose there's red and blue. The red colonel placed 20 troops here, the blue colonel 0 here. Then red colonel wins this one. Again, here the red colonel places 20 here, the blue one 0 here. Red wins that one. Blue invested everything on this field, so he wins this one. But the red colonel wins the other 2. And we have a 4-1 for the red side here. Pretty straightforward, right? But maybe start thinking about how you would play this game against an unknown opponent if you had to play it, because you have to play it, at least 2 of you. And I need 2 volunteers for this exercise. Okay, I think it's always a bit unfair that the people in the front have this bias. So we'll go a little bit to the back here. Yes, can I ask you? That's great. And maybe you? Yes? Please follow me on stage. No cheating, and please don't tell them what to do. Let me just grab my mic for you. Okay, what's your name?
Michael.
Michael, excellent. What's your name?
Tristan.
Tristan, very good. You see, we have these 2, come here maybe. You know, we've prepared this very thing here, and if you could write your name somewhere here, so we know that's your side, and we have another board here for you. And if you could also write your name here. Okay, and now what I would like to ask you to do is, you have 100 troops to distribute. There's a bit of calculation involved here, and we'll help you, because we'll ask you to put 5 numbers, 1 into each of these boxes, make sure they add up to 100, and then we'll see which colonel wins, Colonel Michael or Colonel Tristan, okay? And yeah, please have a go. And if you could write large, so that this is visible from everywhere in the audience. And if you want to cheer them up a little bit, you know, and give them hints and confuse them, that will be fine. Okay, that seems to add up. Okay, that's 55 plus 20 is 57, 80, 100. Very good. That's excellent. Let's give them a round of applause here. And now if you could help me pull these together so that we can actually compare and find out who won the match. Okay. So I see 35 here versus 30 there. Sorry. So that one goes to Tristan. Very good. I see 30 here and 20 here. So this one goes to Michael. I see 25 here and 30 there. So this one goes to Michael. I see 15 here and 5 there, and this one goes to Tristan. And I see 5 here, and I see 5 here, and this is almost as if we had staged it, because that gives a tie for our 2 champion kernels. Very good. Thank you very much. So let's look a little bit at the possible strategies that people can take. And here you see a plot of the type of results that we obtain here. So each of these balls here represents one possible strategy people could have taken. And you may have observed that while in practice it is crucial to pick your numbers on the right battlefields, really all the battlefields are the same. It doesn't matter that this is top left and this is bottom right, right? They're not strategically different. So the way we represent these strategies is we sort the numbers and we put the largest first. For example, there's a strategy here that I don't recommend and that I'm glad nobody picked here, which is to put everything, all your eggs into one basket. That's guaranteed to lose unless your opponent does the same thing, right? Not very smart, and obviously nothing anyone in this group would choose. Now there's other folks who might think 20, 20, 20, 20, 20 is a good distribution, right? Because you distribute everything evenly, and you would definitely win against the 100, 0, 0, 0, 0 guy 4-1. So that seems like a great idea. Now this is where the arrows come in, because you see this strategy places emphasis on 3 of these battlefields with 34, 33, 33, 0, 0, and that's guaranteed to be that one, because it will always win those 3 battles against that one. Now this 20, 20, 20, 20 beats this other one, which is 35, 35, 10, 10, 10, because it will always win the 10, 10, 10 things. But then amazingly, this 35, 35, 10, 10, 10 almost always wins against this one. So we have a circle. This one wins against that one against that, and that one against that. It's cyclic, so there's no perfect strategy. For every strategy, there's a better counter strategy, and that's what makes the game so interesting for us to study. Now here are a couple of results that we found. Interestingly, as I was pointing out, really all battlefields more or less look the same. It's not like one is hilly territory and the other is like a river or something, but they're more or less the same. Yet, if you look at where people place their troops, you'll find that they, on average, and these are the averages for each of the battlefields, they place more on the center than on the sides. It's just a strange effect that maybe only humans can produce, because computers would realize they're all the same and might distribute this, whereas humans show this interesting bias towards the center. And there's also a slight bias to the side, which you might attribute to the fact that most of us, at least in this test, read and write from left to right, which introduces an additional bias. So here's another result that we found, which is kind of reassuring, because what you see here in this plot is the number of games played versus the average score that people obtained. And you can see the more people play, the higher their average score goes, even going up to 60% winning rate. This is reassuring because one might interpret it as if you play more, if you practice more, then you will become better at the game. But you have to be careful here. It is just what we call a correlation. So can we really conclude that that's the case, that the fact that these people have played more means that they play better? Or might it not be that people who were luckier ended up playing more because it was more fun to them, because they won more often? You know, open question, but an interesting basic question about correlation and causation. So much for Kernel Blotto. We'll have a little demo booth that we'll show you over lunch, and there's going to be another game which is called Prediction Square, and which demonstrates another way in which we can make games useful. And in Prediction Square, the idea is that can we use games to help improve web search? Because typically web search, Bing, Google, these web search engines are computationally driven. They're big computers that do things. Now, if we had more personal recommendations, if someone told me that you like a particular web page, wouldn't that be great? Wouldn't that be a better recommendation? And in fact, what this game does is it offers you the chance to take any web page or any topic that you like and judge it, tell people how much you like it on a scale from 0 to 10, tell them why you like it. For example, Lady Gaga, I give her 8.9 and I say that she's a great musician. And then you can challenge your friends to try and predict how well you would like Lady Gaga in this example. And in that way, they can then inform the system about what they think your preferences are. Now, just a little call to action. It would be great if you could come and see the demos over lunch, because we're showing both the Blotto game and this prediction square game. But also, you could really help us with our research. So if you could go to this web page here, apps.facebook.com, MSR Waterloo, and log in there and help us do our research. What you'll find is that you can have different game modes. You can do a quick play where you will be pitted against an arbitrary random opponent, or you can pick friends and challenge them and demonstrate your superior strategic IQ in dealing with these game theoretic and strategic matters. What we'll do then is we'll collect the data that you provide us with, and we will do more analysis, draw conclusions, and what we typically do with such results is we try to present them to the scientific community. We write them up in a report. We talk about this at conferences or other events like this. We try to publish the paper, and in that way, you could become part of the global research game. Similarly, for Prediction Square, it would be great if you could help us. In particular, for Prediction Square, we don't have that many people yet who are playing it. So if I see 700 people here, and if you could go to this page and register and challenge your friends, that would be a fantastic opportunity for us to gather more data and maybe to make web search a better and more personalized experience. All right, thanks, that's it.